Okay, here we've got some questions where we have to start with probabilities and actually work back towards values from a normal distribution. So it tells us we've got a normal distribution, it tells us a mean, it tells us a standard deviation. So we can say that W has a normal distribution with mean 14.1, and because the standard deviation is 1.7, the variance will be 1.7 squared, which I don't need to work out. That's mu, that's sigma squared. But we always like to say what sigma is. So sigma is the standard deviation, and that's just 1.7. Okay, so in question 1, okay, I need to draw the correct diagram for this. And you need to be incredibly careful about the wording. It says the wingspan which will exceed 90% of the population. This could be asked the other way round. It could be asking the wingspan which 90% of the population exceeds, and that's exactly the opposite value. So we've got to be careful. We want a wingspan, okay? It tells us here the probability that the wingspan is less than this value is 0.9. That does help us a little bit. So you always draw your 4 pictures, okay? So we want a 90% probability, so what's easy is we can exclude B and C. Our wingspan has to beat 90% of values. So the values from the population, 90% of them have to be less than a value. Okay, that's going on in picture A because here's the value and it's exceeding all these wingspans from the population. Whereas in part D, here's a wingspan and the population values are bigger than that. So using this hint here makes it a little bit easier that this is the picture I need. Okay, it's picture A. Here's our 0.9. Obviously Z is 0 in the middle. What Z value is this? Well, this is where I have to go to my calculator. So I need to go into distribution. I need inverse normal because we're starting with a p-value and we're ending with a z value, and the area I want was 90%, 0.9. Okay. Press equals a couple of times, so I've got my z-score for that is 1.28. So on here, z value of 1.28, z equals 1.28. But what I want to know is what the wingspan is that corresponds to this z equals 1.28. So I've got to use my formula for z, which is x minus mu over sigma. So I want to know the x, the individual wingspan, so I'm going to leave that as x. I'm going to say that x minus mu is the mean 14.1, over sigma, which is 1.7, has to equal the z value that I've got, which is plus 1.28. My diagram just confirms, yes, it is definitely a positive value for z. So I have to say that x minus 14.1 is 1.28. I'm multiplying by this 1.7. Okay, and then to finish it off, I need to add this 14.1 to both sides. So x is going to equal 1.28 times 1.7 plus the 14.1. And if I do that calculation, here we go, press equals, and we get, as a decimal, 16.276. So I record that as 16.3 centimetres, put the units on. Okay, so we've got a few more, a couple more to do. We want the wingspan which will exceed 20% of the population. So again, the wingspan is the big measurement and the population values have to be less than that. But this time the probability is just 0.2. So I look at my 4 pictures. Okay, this time I want a probability of 0.2, which is less than a half. So it's going to be picture B or picture C. Once again, I want the wingspans to be less than this cutoff value. The wingspan I want is the one that is bigger than 20% of values in the population, so I need picture B. Okay, you draw all 4 pictures and choose the one you need each time. Cross the other ones out. So we've got a probability of 0.2 here. Obviously z is 0 in the middle, and I can see that this will be a negative z-score. So I go back to my calculator and I set myself up with normal CD. Okay, and now, inverse normal, I should say. We're starting with a probability. We want a z value. So the area I'm starting with is an area of 0.2, and it will tell me the z value is minus 0.841, minus 0.84. Makes sense on the diagram that it's negative, minus 0.84. So in dotty 2, I've got z equals minus 0.84, but I know that that is x minus mu over sigma, okay, using the same formula that I used last time. So x minus mu is still 14.1, sigma is still 1.7. So in fact it's exactly the same calculation as I did here. Okay, I multiply by the 1.7 and I add the 14.1, but instead of the 1.28 I had last time, this time I'm going to have x equals minus 0.84. I'm multiplying by the 1.7 and then I'm adding on the 14.1. So I need to do that calculation. Here we go, and it is 12.672, so that's 12.7. And my diagram gives me another reality check. I haven't drawn it very big, which is maybe a mistake. But I know the mean value, the value in the middle is 14.1. So I can see from the diagram I'd expect an answer like this that's lower than the middle value. And similarly in the previous one, this middle value is an x value of 14.1. So this has got to be bigger than 14.1. And sure enough, it was 16.3, so it's on the right side. So build in these kind of reality checks just to make sure that nothing's gone wrong with some kind of sign error. And then for the third one, I've now got to work with the central 95% of the wingspans. So this isn't just a single value. We've done an example a bit like this higher up the page, but let's just do it again. So we've got a central probability of 0.95, which means that the remaining 5%, okay, is shared between the two edges. So in particular, this is 0.025, and this is the other 2.5%, 0.025. So the actual picture that I can use for my look up on my calculator is I can think about all the area to the left of this value. So this is going to be z equals 0. If I combine these two sections, I get a total area here of 0.975. And that's a probability that I can look up. So if I do that on my inverse normal, so let's go into that. So I'll need to look up an area value of this 0.975. And it tells me that the z value there is 1.96 almost exactly. So this is a z of 1.96, and because it's symmetrical, I know that the other one is going to be z equals minus 1.96 on the other side. So I've got plus z equals plus 1.96 and minus 1.96. So all I've got to do is find the actual wingspans that correspond with those. So continuing with dotty 3, the first one is z equals 1.96, which is still x minus 14.1 over 1.7. So that's going to give me x equaling 1.96 times the 1.7, okay, plus the 14.1, and that's going to give me my first x value. So there's the correct calculation, and there's the value, 17.4. And to get the other x value, all I need to do is the same thing, but with the minus 1.96. So if I put a minus in there, I'm going to get the other answer, which is 10.768. So that's 10.8. So that's 10.8. And so I need to say that the two wingspans that I need to be between to get 95% of the population are 10.8 centimeters and 17.4. What am I doing? 17.4 centimeters. Okay, and any other answers I've given, this should have been in centimeters as well, and that one was in centimeters. So I think I've given all of my answers correctly now in the right units. So that's how to do working backwards from probabilities to find values from the population.